Okay, well, I think it would be instructive for us to think about how we might use the parallel condition. So this parallel condition tells me something about the angles in these shapes that I've divided the big triangle into. So my question to you is, how might I use that information? So my clue is that it's going to tell us something about the angles. So can someone point out for me which angles are the same here in this diagram? So in general, if I've got two parallel lines and I've got some transversals through them, then in this little diagram here, which angles are the same? Okay, so the answer is this angle is equal to this angle. Because these two go in the same direction off of the same line. So those are corresponding angles. So if I mark out which angles are the same here, I've got that this angle is equal to this angle, which is equal to this angle, which is also equal to this. And I can also do the same thing for this other set of angles. This is equal to this, which is equal to this, which is equal to this. So this is pretty nice because I've got a comparison between the angles in these shapes. And I've also got some sort of comparison between their lengths, because I've got that this side of this shape is equal to this side, which is equal to this, which is equal to this. Okay, now I want to be comparing the areas between this section that I know about and the rest of the sections. So a nice way to do that would be to know how much larger certain areas are compared to each other. So I'm going to be spoiling it a bit. I mean, there's a couple of ways we could do this. We could actually find the areas of each of these trapeziums, or this triangle and then this trapezium, by using the information that we have. But I think importantly, we know a lot about triangles. And we know a lot about how triangles scale compared to each other. So my question for you guys is, can anyone see sets of similar triangles in here? So remember that similar triangles are triangles that are exactly the same as each other up to scaling, so up to making it bigger or smaller. Okay, well, I think that these triangles look like they're basically the same thing, but one of them is bigger. And then again, it looks like that's the same as this big triangle here by scaling again, which looks like it's also the same as this triangle over here, the huge triangle. But that is just me looking at it. So how can we actually prove that these triangles are exactly the same as each other, but with different lengths? Well, we can use our comparison between angles. So we've got that in each of these triangles, we've got the green angle. The green angles all match up. And then we've also got that the blue angles all match up. And they also share this angle at the very peak, don't they? And so that means that all of these triangles that I've marked out are equiangular, which means that they have all the same angles, and that's enough to prove that they're similar and they're the same as each other up to scaling. So I'm going to use some facts about similar triangles now that I know that. And it's good because I know exactly how much they've scaled. I know that these purple sections are all the same as each other, which tells me exactly how much larger I've made each triangle. And I can use that information in the end to figure out my areas. Okay, so I think what I want to do is compare the areas between, I want to compare the areas between all my similar triangles, because I am interested in getting area in the end. And I know how to compare the shapes now. So we weren't able to compare the shapes one by one, but we know how to compare like the smaller bit to the smallest bit plus the second smallest bit, and so on. So maybe let's just name these areas now. I'm going to call this one Area 1, Area 2, Area 3, and Area 4. So we know what Area 4 is. I mean, Area 3 is. Okay. So for the area of a triangle, I've got the area of a triangle is equal to half times the base times the height. So let's look at what our bases and heights could be in this triangle. I mean, in each of these. So I could draw, let's say, the altitude from here. So this would be like a shared altitude. This would be like the height. And if that was the height, then the bases would be these lines here. So I want to see how these areas change by comparing how the bases and the heights change. Well, what I know about similar triangles is that all of the lengths scale the exact same way, right? So I should be able to show that if all the lengths scale in the exact same way, then since this triangle has gotten bigger by adding another purple bit on, which is the same as this, So I've basically doubled the length. Then the same thing should have happened to my height. My height should have doubled as well. And if you don't believe me, we can actually prove it using equiangularity again. So if I just repeat the same diagram. So remember that I've got these all equal and these all equal. And these are now right angles because I've drawn the altitude. So my claim is that the way in which this has scaled, so this has scaled by doubling, is the same way in which this has scaled. So this has also scaled by doubling. So if I want to actually prove that using facts about similar triangles, I think what everyone's used to is that the sides of similar triangles are in proportion. Okay, so the sides of similar triangles are in proportion, but the intuitive idea that actually all of the lengths in similar triangles scale in the same proportion should be true too. And I can prove this one by just saying that this triangle here is similar to this triangle because it's got the same angles in it. It's got a shared angle here. It's got these two angles the same, and it's got a right angle here. So because these are similar, then that means if my length on this side has doubled, then my length on this side has doubled. So that's really good, because now I know exactly how to compare the heights. So if I call this the height of the smallest triangle x, then I know that my heights of my triangles from biggest to smallest, so triangle, let's just call them triangle 1, triangle 2 for the second smallest, triangle 3 for the third smallest, and triangle 4 for the largest. My height here is equal to x. My height in the second triangle is equal to 2x. My height in the third triangle is 3x. And my height in the biggest one is 4x. And again, that's by using the fact that the heights grow in the same way as the purple sides grow. And I could use a similar proof to show that actually the same thing happens for the bases. So if my base here is y of the smallest triangle, then my base for the second one is 2y. My base for the third one is 3y. My base for the fourth one is 4y. Okay, so this result is something that everyone probably believes because they know that similar triangles are just exactly the same triangle but scaled in all directions by a certain amount. But if you want an actual proof of it, we could use similar triangles again. So let's just draw the diagram one more time just to prove this last bit here. Oh wait, hang on. Well, we've already shown that this triangle is similar to this triangle, which is similar to this triangle, which is similar to this triangle. So the base is growing in the same proportion as this side growing is immediate from this fact that sides of similar triangles are in proportion. So I didn't have to do much proving there. Okay, great. So now that I know how the bases and the heights grow, I can figure out how the areas grow. So let's now just look at the areas of each of these triangles. So for my smallest triangle, my area is half xy, because I've named the height x and I've named the base y. So in comparison, my triangle 2 has an area of half 2x 2y, which is equal to 2xy. Triangle 3 has an area of half 3x 3y, which is equal to 9 on 2xy. Triangle 4 has an area half 4x 4y, which is 8xy. So this is really great because now I know how to compare the areas of the triangles from the smallest to biggest. And what I have here is not exactly the area of one of these triangles, but I can write it in terms of the areas of the triangles that I do know about. So this area is actually the area of the third triangle minus the area, minus the area of the second triangle. So remember, the third triangle is the third biggest. And then the second one is that one. So I know that my area 3 minus area 2 is 225. So that can tell me something about x and y. Whoops. Okay, so I'm going to be using both of these. And I want to see what my area of triangle 3 minus area of triangle 2 is. So if I do some algebra, I've got 9 on 2xy minus 2xy. Which is 5 on 2xy. And like we said, that's equal to 225. So from this, I can actually figure out what xy is equal to. Xy is equal to 2 on 5 times 225, which is 450 divided by 5, which is 90. And let's see, is that going to be enough for us to figure out what the size of our biggest triangle is? So we're trying to find the area of ABC, and ABC is actually our triangle number 4. And to find triangle number 4 area, I know it's 8 lots of xy, but I already just found xy. So even though I don't know the individual values of x and y, I know how to find the area of the biggest triangle now. And so that means that my area, I meant to say that my triangle 4 is actually equal to ABC. And so 8xy is equal to 8 times 90, which is 720. So my area of my triangle 4, which is triangle ABC, is 720. And the answer is 720. So before Michael has a comment about this, do people have any questions about this?
Yeah, so I guess my comment is, I guess if people are having trouble finding this solution, so this is actually, it's not completely routine, even if you know similar triangles. And I think a good way to get started, so the problem solving aspect of this is to draw a nice triangle and try to figure out how the areas work with just the triangle that you drew. Yeah. So you can figure out a lot of things by just kind of, maybe you can make the triangle a right angle triangle even. Okay. And then just trying to figure out how the areas relate to each other. Okay, I might have to split this into a breakout room for us for at least an hour. So just
Mm. So if we did this special case here where ABC is actually right angled, then to compare the heights is actually really easy because now the heights just become the leftmost sides of the similar triangles. So if someone wasn't convinced about whether or not the heights change in the same way as the sides, then they could just look at this special case here.
yeah, sorry to interrupt. I'm just gonna make the breakout rooms for a sec. I just have
Okay.
to